All right, this is section 15.4. This is on Green's theorem. And so what this is let me sort of give it a little intro, just so we can contextualize this. So this is another method, or a method, of evaluating the line integral of a vector field. So far, we have two ways to do something that looks like this. This is a line integral of a vector field. Now, typically you don't get to pick either way. Typically you do it one way or the other, depending on the situation. So we can either parameterize C and do it that way. Say go from there. That was the first way that we went. And this is sort of the last thing you ever want to try, is to parameterize C. The other possibility is to use the fundamental theorem of line integrals. This will only work if the function, the vector field rather, is conservative. Right? So the fundamental theorem of line integrals when f is conservative. So Green's theorem is going to give us yet another method. So Green's theorem is another way. Now, it turns out it's very, very specific. And so what I'll do is I'll give Green's theorem, and when I give it, it should be clear from the description about when it can be used. But if it's not clear, I'll sort of really make it clear. So Green's theorem says the following. So it will only work in 2 dimensions in the xy plane, and it'll only work when C is the edge of a region. Now, to be fair, it can be used in slightly more abstract situations, but I'm going to introduce the theorem as a very sort of fundamental, simple one. So we'll say this. Suppose C is a curve in the xy plane, which forms the, and I'm going to be even more specific, forms the counterclockwise edge of a region R. So visually, the way you want to think about it is that you have a curve C, and that curve is the edge of a region, which I'll shade in, R. And notice C is oriented. I'll make some notes about C in a second. So note here, I haven't given the rest of the theorem yet. I just want to point out these things. C is oriented. In other words, it has a direction. If you like, it has direction counterclockwise. Second note is it forms the complete edge of R, like it goes all the way around. It's closed. C is the closed. Remember, closed means the beginning equals the end. So it's closed and surrounds R. And this is all in the xy plane. So then what it says is, since we're in the xy plane, the vector field that I'm going to have, the f, will only be 2-dimensional. So what it will look like is this. And so what Green's theorem says is that this is equal to the double integral over R of the partial of n with respect to x minus the partial of m with respect to y dA. Now notice the thing that's inside here is a scalar. Let me make a note of that in a different color. So this is like a normal standard double integral. So this guy is a regular double integral. Now I'm going to make a few notes before we do some examples. So first note, let's say notes plural. So the first note is this notation up at the top, the notation right here. This is one of our two notations for line integrals of vector fields. So this can also be written as following, right? Same as the integral over c of m dx. Remember this guy right here means the same as the green arrow up here. So in other words, these two things, these are literally the same thing. And so what Green's theorem says is the same as saying this. That's the first note. Second note is that C must be counterclockwise. So if C is clockwise, we can still use it, but we negate the answer because we're reversing the orientation. And lastly, this is just to emphasize the point, is that C must completely surround R. So just this little picture, if you had a C that was like this, this would not work. So before I do some examples, one thing to consider is when you may use this, because this may be your feeling. You may think that, like, well, you're starting with a line integral, which is a single integral, and you're changing it to a double integral, which may feel like it makes it more complicated, but you're getting rid of a vector field, and you're introducing a nice simple double integral. And so usually the integral you get to is nicer than the one that you started with, the one that you would have done a different way. So here are some examples. So here's a really simple example. Suppose C is the following. So I'm going to make C a little triangle. Say something like this. And so this C will go completely around the triangle. Let's make it say 2, 2. So this is the point 2, 2. Goes counterclockwise. And let's find the integral over C of, say, 2xy dx plus y dy. So just a note, in terms of the two methods that we have so far. So first of all, this is almost certainly not the fundamental theorem of line integrals. The reason is because C is closed, the fundamental theorem of line integrals would automatically give us 0. Because remember what we said is if the vector field is conservative and if the curve is closed, then the integral is automatically 0. So to do Green's theorem, we have to have a closed curve, which means probably, unless I'm just sort of trying to be really sneaky, which won't happen, this will not be a fundamental theorem of line integrals. So you could parameterize C, but if you do that, because C is broken into 3 pieces, you have to use 3 parameterizations. Right? So to parameterize C, we need, well, we would need, because we're not going to do it, we need 3 R's, because C is in 3 pieces. Or 3 segments, if you like. So instead, let's apply Green's theorem. So this would be 3 integrals if we did it that way. So instead, by Green's theorem, this integral that we're trying to do, or that we want to do, this becomes a double integral over R. And so the way to look at what's about to happen is, this is our M, this is our N. And so what we do is we do N sub x, which is 0, minus M sub y, which is 2x. So just to emphasize, this is N sub y minus M sub x. Those are partial derivatives. And in this case, where R, So R is the region that's inside. So let me draw a separate picture of R, because we've sort of changed, right? We've gone to a integral around a curve to like an area integral or a regular double integral. That is our R. And so then, now we're back in the beginning of chapter 14. So now we can see, like, well, look, this is a vertically simple region. So here, I'll put this over here. R is vertically simple. So the result, the x goes from 0 to 2. Remember, this was 2, and this top line is y equals x, because it goes up to 2, 2. So 0 to 2, 0 to x, negative 2x, dy dx. That's a really, really, really nice integral to do, right? That's a really quick integral. So let's just do it quick. Hopefully this will fit nicely. So when I integrate with respect to y, we get this. Plug in these things for the y value, because that's what we integrated with respect to. So again, negative 2x squared minus 0. Integrate this, get negative 2/3 x cubed, 0 to 2, which is negative 2/3 times 2 cubed, and that's the answer. Significantly easier than parameterizing and worrying about all that stuff. And the key things to see here, so let me mark this up a bit, let's use, say, green, is that we went from a line integral right here to, like, if you like, this is kind of like a region integral. Right, the original curve here, C, is counterclockwise. We get this new double integral, we iterate it, we finish it. So let me do a second example real quick. I'll do a couple more, because there are some other comments I want to make. All right, second example, very different. Let's say, suppose C is, so in this case we'll do, say, a quarter circle, radius 3. And so C, just to be clear, C is the edge of a quarter circle. Right, it's like a little piece of wire that goes this way. We're going to make this clockwise. We're going to find, so I'll give slightly different notation. The integral over C, I'll use the other notation. I'll give the standard vector field notation. So let's say 4y squared I, that's a rather crazy I, plus, say, x j dot dr. So again, just to emphasize, this is our m, this is our n. And so we'll do by Green's theorem. This becomes the double integral over r. Now, actually, let me sort of make a fix of that. Right? So because the C is because the C is clockwise, and I want it to be counterclockwise, we negate the entire package. So I'll mark that in a second as to why that is, but that's because we started with a clockwise C. And so then we negate it, and then we do Green's theorem, which says the double integral over r of n sub x, which is 1, minus m sub y, which is 8y, dA. So let me mark this up a bit, just so we're clear. This guy is because C is clockwise. This is our n sub x minus m sub y right in there. So then we get to this, and then we look at our r. So this is, just to be clear, this is where r is now this. So r is now the filled in quarter circle. That thing. Still radius 3. And so for this r, I would want to use polar, because it's really nice in polar. So we'll use polar for r. So what we get now is negative 0 to pi over 2, 0 to 3, that's the parameterization for r. 1 minus 8, we replace y by r sine theta. We put in the polar r, dr d theta. So again, just a little clarification. I'm not going to do this to completion. This is 1 minus 8y. This is our polar r. Remember, that's the guy that always gets put in when we go to polar coordinates. And then from then on out, we evaluate. So the big thing to note here, well, two things to note. Right, you can use polar if it's appropriate. And if C is clockwise, negate. So let me do one more simple one to point something out, and then I'll do a slightly more, make a few more closing notes. So for example, I want to make this one sort of sneaky. So suppose C is this. So I'm going to make it another, well, let's see. Let's make it like a trapezoid. I'll actually make it slightly awkward, just for fun and excitement. So we'll go up from 0, 0 to 1, 2, then we'll go over to 3, 2, and then we'll go down to 5, 0. Then we'll go back along the bottom. So again, this C is completely closed up. Let me really emphasize what this C is. It's this whole thing. And we'll make it counterclockwise, sort of the nice direction. What we'll do is we'll find the integral over C of, say, 4y dx minus 17x dy. So by Green's theorem, so one thing to note here, it's double integral over r. So, and I did this sort of on purpose, is the m here is pretty clear. The n here has to include the minus, because the official theorem said m dx plus n dy. So the n includes the minus. So please keep that in mind. So when I do this next bit, I'm going to do n sub x, which is negative 17, minus m sub y. So again, this is our n sub x minus m sub y. Now, notice when you do this, you sort of get something nice. You get the integral over r of negative 21 dA. Now, you might look at this, you might say, like, okay, let's parameterize r. And then, just to be clear, the r in this case is now sort of a trapezoidal region. I'm dividing it up with vertical lines just to help us see something. This is at 2, this is at 1, this is at 3, this is at 5. So the thing I want us to see is, you notice that integrand, the thing inside the integral sign, is a constant. Now, that might not sort of strike any particular chord, but constants can be pulled out. And so this becomes negative 21 integral over r of 1 dA. Now, whenever you integrate the number 1 over a region, we've seen this come up a few times. When you integrate the number 1 with a triple integral, you get volume. When you integrate the number 1 with a double integral, you get area. So this actually gives negative 21 multiplied by the area of r. And again, r is a trapezoid. Now, in this case, this is really handy. This won't always be the case. I'll make a comment about that in a second. But because r is a trapezoid, we can work out its area, right? It's made up of 2 triangles and a square in this case. Here, it's easy. So I'll just do it into 3 pieces. Each triangle is half base times height, right? So for the first triangle, the base is 1, the height is 2. So 1/2 base times height, Second bit is a rectangle. It's a square, in fact. It's 2 by 2. The third one is 1/2 base times height. So what's happening here is this area is this area, this area is this area, and this area is that area. So it turns out, because we got a constant for the result, we can pull it out, and because the resulting R has an area that we know, that's familiar to us, we can shortcut it. So that doesn't always happen. But let me write those comments down. So then the two notes that go with this are to note when the integrand, in other words, the n sub x minus m sub y is a constant, we can pull it out to get a constant times the double integral over R of 1 dA. Right? And this thing is the area of R. Now, this is only useful when the area of R is something that you know, right? If R is a cardioid or some weird shape that you don't know the area of, then this is no help. You still have to parameterize, right? So this is nice. This is useful only when R is nice, meaning known area. Right, so, for example, if R were a cardioid, then we still need to iterate it, because we don't have a generic formula for the area of a cardioid, right? There's no nice one that we know. Whereas the area of a trapezoid, triangle, circle, semicircle, quarter circle, triangle, all those things we can do. And so, final note is that Green's theorem is actually a bit more flexible. It'll work for regions with holes, or rather, let me put it this way. We won't see this much, but it's sort of good to mention. Green's theorem will also work. This is going to sound like a mouthful when I say it. When C is the edge of R, when R is a region with holes, as long as, let me say it this way, as long as the holes have clockwise orientation. So this is a bit confusing. Let me just sort of finish with one example that uses this, although it won't come up much, so if this seems a bit weird, don't really panic. So for example, so this is going to be a bit weird. Suppose C is the following. So C is going to be made up of, say, two curves. Right? So we'll just make it simple, though. We'll sort of make it circular. This will be radius 2, this will be 1 in here, and so C on the outside will go here, on the inside will go here. So notice on the outside it's counterclockwise, on the inside it's clockwise. So you might look at this and say, well, which one of these is C? And the answer is C is both. They're disconnected, but that's okay. Right? C is both of these. You could think about them as C1 and C2 separately if you like, but let's suppose that's our C, and suppose we want the integral over C of, say, y squared dx plus y dy. So by Green's theorem, this is equal to the integral over R. So again, we're going to just mark this up. This is our m, this is our n. So we're going to do n sub x, which is 0, minus m sub y. This is our n sub x minus m sub y. And let me draw R. This is where where R is, and then it'll help us see what's going on with the counterclockwise-ness of all of this. So R is this washer shape. And so if you notice, the edge of R is in two pieces, right? It's the outer piece and the inner piece. And the outer, and both of those edges together make C, right? So this is C up here. So R's edge has two pieces. Together, they are C. On the outside edge, I go counterclockwise, right? So outer edge is counterclockwise. Inner edge is clockwise. So Green's theorem has this sort of exception. So basically what's happening loosely is you're doing the outside and you're subtracting the inside loosely. And so to subtract the inside, you have the opposite orientation. It's a little more technical than that. That might give you an idea about why the orientation has to change. But the practical upshot of it all is this is now a nice annulus. I could do polar. Theta goes from 0 to 2 pi. R goes from 1 to 2. Inner radius to outer radius. Negative 2. Y is R sine theta. Polar R dr d theta. And then just evaluate. So we won't do many of these. We'll tend to stick with simple, like elementary looking regions. Nothing as weird as this, just to make sure we have Green's theorem down. So that is it. That's the end of Green's theorem. Fairly short section.